All right. Thank you, Peter. Do this. First, some shameless advertising. There are posters out front on a summer school and workshop that Joel Premack and I are organizing on some of the things that you just heard Dan talk about and I will talk about, and that overlap with a number of the issues in, for example, galaxy formation physics that we talked about earlier. Okay, so why are the neutron star merger and core collapse supernova environments so sensitive to neutrino flavor and spin physics? In a nutshell, the answer is that core collapse supernovae are cold, highly electron-lepton number degenerate systems. Because of that, they're exquisitely sensitive to lepton number violating processes. That's why. And also, as Dan just showed you, in core collapse supernovae, effectively all the gravitational binding energy, all the energy in the problem is in the neutrino fields. And so in the collapse, you're going to generate something of order 10 to the 58 neutrinos. Okay? And so we know from direct modeling that there can be macroscopic effects in the supernova physics or in the signal we would expect from a supernova neutrino burst stemming from flavor oscillations, and those are very sensitive to neutrino mass hierarchy, as I'll show you, and spin coherence. So when I talk about spin in this talk, I'm going to talk, I mean the spin orientation of the neutrino, i.e. whether it's a neutrino or an antineutrino. Remember that neutrinos are left-handed things. Their spin a half angular momentum points opposite to their propagation direction. And the antineutrino is the other way around. It's a right-handed thing, and its spin a half angular momentum points along its propagation direction, its momentum direction. So that spin flip is equivalent, at least for Majorana neutrinos, to changing a neutrino into an antineutrino or vice versa. Okay? That's important because if I could show in cartoon fashion some of the issues that Dan just talked about, this is a cartoon, but the nucleosynthesis ejecta, for example, can depend very sensitively on the mix of neutrinos and antineutrinos, effectively because the competition between these processes sets a key parameter for nucleosynthesis, the neutron-to-proton ratio. We know that flavor oscillations, changing the flavors of neutrinos between electron, muon, and tau type, will go on over a significant region in the supernova. Okay, and also that could affect what we will get for a signal. Okay, so to summarize where we were, Dan just gave a nice overview of, you saw a lot of very sophisticated multidimensional radiation hydrodynamics, Boltzmann neutrino transport, in some cases very detailed microphysics and equations of state. And that's kind of the computational state of the art now in looking at compact object mergers and stellar collapse. But our understanding of the effects of non-zero neutrino mass, and we know that neutrinos have non-zero masses, that is through flavor oscillations and the spin flip, changing neutrinos to antineutrinos, though our calculations of that process are numerically sophisticated, they're in some sense quite crude, both in the physics that they incorporate and in the way they can be incorporated or not be incorporated into real supernova simulations. I think if we try to marry these two pieces of physics right now, we would be well beyond what one can do at the exascale. So we're going to have to learn and feel our way through this as we learn about what physics is important in flavor transformation. I'm pretty confident we'll be able to make approximations that will allow us to, when we get to the exascale, to model at least the important parts of this physics. So that's where we're going towards the exascale. Bottom line, or second to the bottom line, there are unsettled issues in the story of supernova neutrinos. We just don't know some things. One thing we can say for certain now is that the current collapse and merger simulations leave out many of the features of neutrino mass and flavor and spin physics that we know are there. Whether or not they're important, we don't know yet. So here's the quintessential issue that's different in this astrophysical simulation physics and numerical physics than the other things you've heard about today. If we want to follow flavor neutrino flavor and spin, i.e. neutrinos and antineutrinos, we have to follow quantum mechanical phases. And these are high-frequency complex amplitudes. Can be very high frequency. So fundamentally, numerically, it's very difficult. You may have, over some relatively small macroscopic length scale, some huge number of oscillations in these phases. And interference between these phases that has to be followed. So this is the essential difference, in my view, between the neutrino flavor spin astrophysical simulations and conventional radiation hydro treatments. Okay? So there are lots of experiments that have been done over the past 15 years. There's really been an experimental revolution in neutrino physics. And the main takeaway message from the experiments from the astrophysicist standpoint is that the neutrinos' energy eigenstates, that is the mass states, are not the same, they're not coincident with the weak interaction or flavor eigenstates that determine how the neutrinos interact with matter, electron, muon, and tau. Okay, what do we know and what do we not know about neutrinos? Well, we know the mass squared differences, just defined this way, but we don't know the absolute masses. We don't even know the hierarchy, whether we have the normal mass hierarchy with this ordering, with the solar doublet on the bottom or the solar doublet on top and the inverted mass hierarchy. But, you know, this is quantum mechanics, coherent, so there's a unitary transformation between the energy eigenstates, the mass states, and the weak interaction, the flavor states, and you can represent that as a series of rotations. So that gives 4 parameters to that unitary transformation, 3 angles, and a CP violating phase. And the experiments have measured all these things. They've measured the angles. Now, we don't know the CP violating phase, but it's irrelevant for what we're talking about here because the matter effects in neutrino in the supernova problem are effectively maximally CP violating. So we don't need it. So this is settled science. And this physics is there. And we don't quite know how to model it. So this is the relation between neutrino flavor and masses in vacuum. In medium, it's a different story. Neutrinos can scatter on any particles that carry weak charge, including other neutrinos. And those generates potentials then that can make neutrinos change their flavors. Kind of like photons acquire an index of refraction when traveling through a transparent medium like glass. But unlike for photons, in the neutrino case, the potentials that govern how a neutrino changes its flavor depend on the flavor states of the other neutrinos. So the problem is fiercely nonlinear. So let me remind you how a quantum mechanical system evolves. These are the rules. You learn this at your mother's knee in Quantum 101, right? When you make a measurement, you have to get an eigenvalue for the system. And as the neutrino propagates along, as we just saw, it's some coherent superposition of flavor states. So it's a little quantum mechanical system. Moreover, when you get the eigenvalue, you collapse the system into the corresponding eigenstate. Okay? Moreover, there are 2 ways you learn that quantum systems evolve in time. One is a smooth, continuous evolution in time, a Schrödinger equation. The other is an abrupt process, measurement. You measure something and it collapses the state a la rule number 1. Okay. The neutrino flavor problem in supernovae and in mergers forces us to seek a unified treatment of these 2 different things. They really aren't different, of course. If you knew what the fundamental microscopic interactions were, you could understand this and this as 2 parts of the same thing. So a treatment that does that is called the quantum kinetic equation, and that's what we seek. Now, recently, my student Alexei Vlasenko and Vincenzo Cirigliano at LANL have, for the first time, derived the quantum kinetic equations from the ground up, from essentially fundamental quantum field theory and just standard model physics. And this is kind of a cartoon for what it looks like. Some derivative operator, some Hamiltonian that gives the interactions of the neutrinos with matter, and then something that we discovered in this. This F here is just a density operator. So the diagonal pieces of this give the neutrino densities of electron, muon, and tau flavor. The off-diagonal pieces in those density operators give the quantum mechanical correlations. Okay? But in this, we discovered that there's a new dynamical quantity, also a 3 by 3 complex matrix, that encodes spin. Okay? So we can take the low density limit of that, and indeed it looks like a Schrödinger equation. Take the high density limit, where scattering is very significant and washes out quantum mechanical phases, and it looks like a Boltzmann equation that we would treat in standard models. In fact, this is great because the way our paradigm now for modeling core collapse supernovae is down in the core, we model the neutrinos with the Boltzmann equation and ignore flavor and spin. And out in the envelope, we look at the Schrödinger-like evolution, and we see lots of interesting things. Okay? So our current paradigm relies on a separation of these two processes, and we know that we can't do that. Our simulations now show that even a small amount of scattering feeds back here, and this feeds back there, and there are certain regimes in the core where we can't make this separation of scales, where we have to somehow grab the quantum kinetic equation by the horns and solve it. If we look at just the Schrödinger-like evolution of neutrinos out in the envelope of the star, then we can do that. We get collective neutrino flavor transformation. Neutrinos come from the core. They cut each other up. They tell each other what's happening. And the net result is you get wonderful collective neutrino oscillations, which I can tell you about later. Okay? However, and I'll finish with this slide, which is a fairly complicated slide, and I apologize for that, but there's no way around it. So if I look at this quantum kinetic equation that Vlasenko and Trigliano et al. Have derived, I can make it actually a 6 by 6 formulation, where this script F here is those two density operators that I told you about before, one for neutrinos, one for antineutrinos. Those are both 3 by 3. There's our spin quantity that's also a 3 by 3 operator. So each of these Fs exists at each location bin and momentum bin, and they're a 3 by 3 matrix. The diagonal elements give the densities of, say, electron, muon, and tau flavored neutrinos, and the off-diagonal pieces give the quantum mechanical correlations. And the collision term, there's a derivative term, there's an interaction term, and there's a collision term. Collision term is also 6 by 6. And this matter Hamiltonian now, that also encodes neutrino-neutrino scattering, has a piece for neutrinos, 3 by 3, piece for antineutrinos, 3 by 3, and now a term that couples the two. It couples neutrinos and antineutrinos. So again, if we take the Boltzmann limit, the collision term mixes different energies and flavor states, averaging out all the off-diagonal terms, no coherence, we get the Boltzmann equation. Okay. Likewise, if you take the coherent limit, where the potentials that the neutrino sees from forward scattering are very small compared to rest masses, we can drop all these other terms, we get the Schrödinger equation again. But if I take the bull by the horns and look at the structure of this equation, this was a kind of a shocker to us, that it shows that even if the collision term is 0 and the evolution is completely coherent, that these terms can cause neutrinos to change to antineutrinos and vice versa. You might say, well, great, but these terms are very tiny. They look something like this. Effectively, something that goes like the magnetic version of the weak interaction, which is small. Remember, the weak interaction is 20 orders of magnitude weaker than the electromagnetic interaction, multiplied by a term that looks like the rest mass divided by the energy. And the energies are 10 MeV. These masses are something less than 1/10 of an electron volt. So that term right there is 10 to the minus 8. So you might think, these are tiny, and I can ignore them. The problem is that in the matter in the supernova, you could get situations where these diagonal terms vanish. And no matter how small that term is, it can be in control of what happens. So I left you at the beginning of this talk pointing out that the ratio of neutrinos and antineutrinos in these environments is extremely important. And so we don't really know how to model this, but in the drive to get towards the exascale, we're going to have to deal with this, I think, at least in some cases.